Hello, everyone. On behalf of my colleagues, welcome to this month's talk from the Johns Hopkins Institute for Assured Autonomy seminar series, co-sponsored by the Computer Science Department of the Whitening School of Engineering. Each month, we host a talk on research topics at the intersection of assurance and autonomy. This seminar will be recorded. Today's speaker is Professor Cynthia Rudin. Dr. Cynthia Rudin is a professor of computer science, electrical and computer engineering, statistical science, mathematics, and biostatics and bioinformatics at Duke University. She directs the Interpretable Machine Learning Lab, whose goal is to design predictive models with reasoning processes that are understandable to humans. Her lab applies machine learning in many areas, such as healthcare, criminal justice, and energy reliability. She holds an undergraduate degree from the University of Buffalo and a PhD from Princeton University. Dr. Rudin is the recipient of the 2022 Squirrel AI Award for Artificial Intelligence for the Benefit of Humanity from the Association for the Advancement of Artificial Intelligence, that's AAAI. This award is the most prestigious award in the field of artificial intelligence, similar only to world-renowned recognition such as the Nobel Prize and the Turing Award. It carries a monetary reward at the $1 million level. Professor Rudin is also a three-time winner of the Inform's Innovative Applications in the Analytics Award, was named one of the top 40 under 40 by Poets and Quants in 2015, was named by the BusinessInsider.com as one of the 12 most impressive professors at MIT in 2015. She's a fellow of the American Statistical Association, the Institute of Mathematical Statistics, and AAAI. Today, Dr. Rudin will talk about interpretable neural networks for computer vision, clinical decisions that are computer-aided, not automated. Welcome, Cynthia, and over to you.
Thanks. I'm just going to share my screen here. Great. Okay, so we should be avoiding automated decisions as much as we possibly can for high-stakes decisions. But that's hard because it means that humans and computers have to work together and they have to understand each other. But computers don't always behave the way we want them to, and it's not always easy to figure out what they're doing. Okay, so what happens when we use a black box? So I have here a couple of articles. This one is about air quality during the wildfires of 2018. And Google had replaced the Environmental Protection Agency's trustworthy air quality pollution model with a proprietary model from the company Breezometer. And that model told people that it was safe to go outside on days when it was not. And that could easily put people in danger. And this article here is about how FDA approved deep learning models for detecting intracranial hemorrhages are not performing well, and no one knows why. Okay, now I'm talking about medical decisions here, and the one thing anyone knows when they start to work with medical data is that it is really, really messy, and it is really easy for a machine learning model to get confused. So I want to introduce you to Clever Hans. Hans is a horse. Hans really seemed to be quite clever. He could answer questions like, if the 8th day of the month comes on a Tuesday, what is the date of the following Friday? And Hans would answer by tapping his hoof 11 times. And his owner had no idea how he was doing this, and nobody else had any idea how he was doing this, but it turns out that Hans was simply looking at the level of stress in the owner's face, like, you know, and when the owner would relax, Hans would stop tapping his hoof. And this is exactly the kind of problem that we don't want in medical imaging. We want an AI system to reason about an image in a way we could actually trust. All right, so why is interpretability important in all this? So interpretability helps you detect confounding, like the Clever Hans phenomenon. Interpretability helps with high-stakes decisions where a human really needs to know the reasoning process. Interpretability helps you troubleshoot, like, you know, is it going to work if I switch equipment? If it's a black box, I don't know. Is it going to work for all types of patients? Well, it's a black box, I don't know. Can I check if it's working on my current patient? Well, if I don't understand the reasoning process, then I don't know. And is the information that I fed into the system correct? And so, you know, also, issues of responsibility, right? It is the doctor's responsibility to make a good decision. And you know, if you use a black box, you actually take that decision-making ability away from the doctor. And so now it's the black box making the decision. And so, you know, the use of black box models, it just makes all of these problems worse. Like black box models, they just turn computer-aided decisions into automated decisions. And what we really want here is for the computer to do what it does best, like crunch data to find patterns. And we want to preserve the human's like systems level way of thinking about problems. Okay, so now a lot of people have been trying to explain deep neural networks. And the thing is, what they try to do is try to figure out where the deep neural network is looking in order to make its decision. And the thing is, deep neural networks are not actually designed to explain their decisions. And so when you ask them to do that, it doesn't really work. And a lot of people really love these saliency maps, which are just highlighting in the image where the network is looking, but I actually don't find them sufficient. I find them to be really incomplete explanations of what's actually going on. So for instance, here's an explanation from a saliency map as to why the neural network is classifying this image as a Siberian husky. And it's highlighting the part of the image you'd think would be useful for classifying a Siberian husky, and you think, okay, maybe I trust the network. But then you ask the network, okay, well, why do you classify this image as a musical instrument? And it gives you the exact same reasoning process, which is I'm looking here. It's the same spot. So it's just not giving you any information about what the reasoning process actually is, right? It's just really incomplete information. And I'm alarmed that there's a lot of work in radiology right now on attention maps. People are they're designing literally hundreds of techniques to do exactly what I'm showing you, is just to highlight the part of the image that the network is looking at. Anyway, so I finally, at some point, got sick of all of this nonsense where people were sort of explaining these black box models in these really insufficient ways. So I wrote this paper saying, stop explaining black box machine learning models for high stakes decisions and use interpretable models instead. And I made this point in the paper, which is that if you have tabular data, so no images, just tabular data, you should be using, you can use methods like decision trees or linear additive models or scoring systems. You don't need neural networks. Whereas for raw data, I was recommending interpretable neural networks, which are different than just explaining black boxes with saliency maps. So let me explain to you a little bit more about why I am making this suggestion. So there's really two main types of data that we end up dealing with in machine learning, and they represent very, very different types of problems. So if you naturally have a good data representation, you're going to be working with tabular data, and in that case, you have features that are categorical or real valued, and I've given like a healthcare example here. And for those types of data problems, all the machine learning methods tend to perform very similarly. So you're not really getting a benefit from a very complex model, you're not really getting a benefit from something like a neural network. So there's not really much point in sort of doing that. Whereas with raw data, like images or sound waves or large amounts of text, the only method right now that's working is a neural network. And that doesn't mean that it can't be interpretable, but we have to think a little more carefully about what interpretability means than we do when we're dealing with tabular data. So for tabular data, as I said, with minor preprocessing, all the methods tend to have similar performance, and that opens up an opportunity to create very, very sparse models like decision trees or scoring systems that a human can even often memorize. Okay, so I want to give you an example of these tabular data problems. And then I'm going to switch over and spend the rest of the talk discussing what interpretable neural networks could possibly mean. Okay, so I'm going to give you an example now on the tabular data side. So this is an example of preventing brain damage in critically ill patients. So let's say that you have an aneurysm and it bursts. So you have a hemorrhage in your brain where you have blood sort of leaking into your brain, kind of like a blood explosion in your brain. And you would go immediately to get to the hospital. You get surgery, you'd be placed in the intensive care unit, and you would have EEG monitors placed all over your head And those monitors are detecting for seizure-like activity, because seizures are common in these kinds of patients. So about 20% of patients get them. These seizures they cause brain damage, they cause death. They are often more problematic than the actual thing you came in with. And the only way to detect seizures are through EEG monitoring, because these seizures are subclinical. It's not like the patient shaking or anything. It's just what's going on inside the patient's brain. And doctors will do a lot to prevent the patient from getting a seizure. They'll give the patient drugs to even shut off part of the patient's brain to prevent that. Okay, so the thing is that you need EEG monitors to detect seizures. Those monitors, there's not enough to go around. There's not enough doctors to read the monitors. And so people stay on the monitors kind of way too long, and then people who need them don't get them. So we have to really be able to predict seizures in advance so that we know how to allocate these monitors. So I worked with neurologists to design the 2 helps 2B score, which predicts seizures within 6 hours. And this model is now widely used in hospitals, and it's small enough that it can fit on a PowerPoint slide, but it's as powerful as our best black box machine learning models. And if you take a look at this, it's you enter points in, and then the points add up to a score, and the score translates into a risk of seizure. Now, it's called 2 helps 2B because it's 2 HELPS and then 2 points to the V. So the doctors can memorize the whole model just by knowing its name. Now, this model is a machine learning model. It was not created by doctors. It was created by data fed into a machine learning algorithm. I know it looks like a rule of thumb, but it's actually a full-blown machine learning model. It's just as accurate as black box models. It doesn't force you to trust it, right? Black box models sort of force you to trust them. Here, the doctors can decide for themselves whether they want to trust it. Doctors can also calibrate the score with information not in the database, because there's always something unique about a patient, and the doctor might want to incorporate that into the score. So they could say like, oh, that thing about that patient that's not in the database, I'll give them a point for that. And then the score can be explained to non-physicians. So you can explain like why someone's being taken off of EEG monitoring, for instance. And now I know that it looks like just a linear model with just 6 factors, but these 6 factors were chosen from a large database of over 70 factors. And like this 2 Hertz, like that was chosen by the model, and all of these coefficients were chosen by the model. And there's actually a combinatorial explosion in the number of possible models that you could choose from. And so our optimization method had to actually go in and choose, make all of these decisions. So even though it looks like a very simple rule of thumb you can memorize, that was how we designed it. It's by design that way. The algorithm that does it is quite intense. All right, now so far, 2 helps 2B has been validated on an independent multi-center cohort. So what I'm showing you here is the data in blue that we originally designed the model from, and this is predicted versus true probability of seizure. So you really want to be kind of like along the diagonal. And then green is the validation study. And so as you can see, it generalized nicely across different hospitals. And I was not involved in the validation study. This was done by neurologists. And so far, 2 helps 2B has been implemented at several different hospitals. And it's resulted in a substantial reduction in the duration of EEG monitoring per patient, which means that the doctors were able to monitor quite a few more patients, so 2.82 times more patients than before, which, according to the doctors, helps them reduce brain damage and save lives. And so, the reason why we could use it is because it's interpretable, right? People can understand it. So it's a rare example of a machine learning model that's used in a very, very high stakes decision-making setting. All right, so I've given you an example for tabular data, and now I want to go and ask this more difficult question, which is sort of, what is an interpretable neural network? What does that actually mean? You can't define interpretability in terms of, here for the tabular data problem, I defined it in terms of like sparsity and so on. Here, you can't create a sparse model on pixels. That doesn't make any sense. That's not interpretable. So, what does interpretability actually mean here? So we've been making some attempts to define what interpretability could mean for computer vision. So I want to show you, I'm going to show you two approaches in the remainder of the talk. And the first approach is a neural network that does case-based reasoning. Okay? So case-based reasoning is kind of like what Dr. House would do. I don't know how many of you watch the old show House. I love that show. So that in that show, Dr. House, he would look at a patient and he would say, that patient has a green foot. You know, I've seen a patient with a green foot. That patient had chilblains, and so, you know, maybe that's what it is. But, you know, but also this patient has a weird heart condition, and he reminds me of this other patient that had a similar heart condition. So he would sort of reason about a current case with relation to past cases. Okay, so let me show you the way our network reasons here. So here's our network explaining to me why it thinks this bird looks like a clay-colored sparrow. Okay, and I love working on the bird watching data because I know nothing about birds. Okay, so here's this bird, and the network says, I think this part of the bird, and here I'm just highlighting it two different ways. Okay, I think this part of the bird looks like this part of that bird. And this is a prototypical clay-colored sparrow that I have in my training set, okay? And not only that, I think this part of the bird here, like the little edge of the feather there in the belly, that looks like this part of this bird. And this is a prototypical clay-colored sparrow. And I think this looks like that, and I think this looks like that. Now, in this network, every step can be checked by a human, okay? So all the calculations are either this looks like that, so that a human can use their eye to determine whether they indeed agree that this looks like that, or it's adding up a bunch of numbers. It's like a linear model, okay? So every step in this network is either a visual comparison or it is something that you add up, okay? Because every one of these comparisons gives you a real valued score, and then the scores get added up. Okay, now because the network does these comparisons, like this looks like that, and this looks like that, and this looks like that, we called the paper This Looks Like That. And what it does is it allows you to take your favorite black box deep neural network and convert it into one of these case-based reasoning networks. It adds a prototype layer just before the last fully connected layer of your favorite black box, which forces the network to do this kind of case-based reasoning. And the prototypes are all learned during training, and the way we compare parts of images to each other, that's all learned during training as well. So it's a completely supervised, standard supervised classification setup. You just put, you know, the features and the labels in, and it just has to reason this way because of the way we've constrained the network. So let me just give you more detail about how it works. So you have your favorite black box deep neural network, convolutional neural network, and then you just add this layer before the last fully connected layer that forces the network to do these comparisons to the prototypes. Okay, so I'm going to give you more detail on how this whole part of the network actually operates, okay? All the details on this whole computation. So here is the network explaining to me why it classified this bird as a red-bellied woodpecker. So the network says, I think this part of the bird looks like this part of that bird. This bird is one of 20 prototypes for the red-bellied woodpecker class that the network chose during training. And then it provides a score for this comparison, which is 6.499. Now that's a very high score relative to the other scores. And the reason is because this bird has a bright red head. I don't know if you noticed that, but the network's like, blah, this is why I recognize this. And it's looking at sort of, you know, you can see the orangey color here, and then the white, it's kind of like C-shaped there, and like a little black bit in the middle. So it's really saying like, no, this is really, I think so. It's very similar. This is very similar to that. And then this other number here is how similar or how important this prototype is for the red-bellied woodpecker class. So each of the 20 prototypes for red-bellied woodpecker class have a class connection weight. And then these numbers get multiplied together And this is the score that comes from this comparison right here. Okay, so it does 20 comparisons per class, gets 20 numbers, and adds them up. And this is the score for the red-bellied woodpecker class. And it does this for all of the different classes. And in this case, the network says, well, the most evidence I have is for the red-bellied woodpecker class. I have 32 points. And the next highest class is the red-cocketed woodpecker. And here, well, I got some points from looking at the feathers, but since red-cocketed woodpeckers don't seem to have red heads, I can't gather that many points, and so the evidence is a lot less for this class. Now, the network does not always get everything right. So here's an example where it actually got it wrong. So here we used a base model that is DenseNet 161, and then we asked it to classify this bird, and it classified it incorrectly. And so we looked at what happened here, and it's really looking at kind of the bird's eye. So it sort of, correctly classified that. I mean, this is the class that it should be, but it's not. This is it was incorrectly classified as a prothonotary warbler instead of a Wilson's warbler. Now, for the Wilson's warbler class, it looked at the eye and the feathers here, whereas for the prothonotary warbler, it's looking at sort of the head and the kind of the colors here. And to me, to be honest, it actually really looks like prothonotary warbler. So we were thinking like, okay, well, what happened here? And then when we switched the base network to a different base network, it got it correct. And we looked again at the reasoning process, and you can see that this VGG16 proto-PNet is looking still at the bird's sort of eyes and its beak, and it's clearly avoiding the bird's head. So I think what's happening is that this bird might be like a baby Wilson's warbler, and so it doesn't like have the black spot that's like characteristic of these Wilson's warblers. And so that's kind of why it looks like a prothonotary warbler to the network. And maybe to people like me who don't know anything about birds. So anyway, we've been using the proto-PNet on the Cub 200 dataset, which is a benchmark dataset in computer vision. And this dataset has 200 classes of birds. This is where the deepest of the deep neural networks compete with each other. And the original black box accuracy was between these numbers when we did this experiment. And then when we made them all proto-PNets, we still got accuracy within the same range. And then when we stacked the interpretable networks together, we actually got an accuracy that was sort of better than all of them. And it's still interpretable because it's still reasoning about birds in terms of like doing case-based reasoning. So what I'm saying is that, even for computer vision, we can still have an interpretable model of the same level of accuracy as a black box. So I'm gonna just pause here for a couple of questions here and answer those, and then I'll go on and talk to you about the application that we have for this model. Okay, so the question is, the first one that I'm gonna hit at is, how do the boxes for comparison get chosen? Okay, so it's actually, what I was actually showing you is, these heat maps, and then we put a little box around the heat map. So that's how it happens. Is like what we're doing is we create heat maps, right? The network creates heat map, and then we put a little box around it. So it's not just saliency. It's not just showing you where it's looking. It's telling you what it's doing with that part of the image. It's comparing it to another part of another image. Okay, and then do you think this can be extended to other data modalities and classification problems? So it has already been extended to other modalities. So there was a wonderful paper that my group didn't write, but that I was so jealous of. Like I was thinking, this is a really lovely paper. I wish we had written this. But they extended it to sound waves and did case-based reasoning on sound waves. But yes, you can definitely extend it to other types of problems, and I'm going to show you kind of how we extended it to radiology problems in a minute. Okay, how can we be certain that the case-based reasoning explanation is exhaustive, that it's not basing its classification system on some info not derived from the prototype image, like it's looking at the color of grass in the input image? So Okay, the grass in the input image doesn't match the grass in the prototype image. Also, how vulnerable is the approach to adversarial examples, whether deliberate or accidental examples? So this is a good question. So I'll remark that first, our network does sometimes look at grass, right, to identify a bird, or water. For instance, with seabirds, we found that it definitely uses the information about sea to determine whether the bird is a seabird. Now, luckily for us, that's something we can see because it's interpretable. And so we can either remove the C prototypes, it's just like blue. We can just literally remove those prototypes so that it doesn't use those prototypes. Or, we can tell it in other ways to focus on certain parts of the image, which I'll talk about in a minute because we had this problem for radiology. And then how robust is it to adversarial examples? So that's something that goes beyond what we're doing. I know that a couple of computer, security experts have kind of looked at this, but I don't know kind of what they're doing. But I suspect that you have to do the same kinds of things to this network to make it robust as you do for sort of other types of neural networks that have to deal with robustness. But I'm hopeful that because every calculation is like a visual comparison, that if this doesn't look like that, then the human can say, oh, I know what went wrong. There's some adversarial example that's perturbing this type of comparison, and then it's more easy to troubleshoot. Okay, I think I'm going to keep going, and then I'll answer more questions a bit later. Okay, so let me keep going here. And we were wondering where it might be useful, and we decided to work on digital mammography, right? So the reason why we chose to do this is because I have a friend who had breast cancer, and I also have connections to our medical physics group. And so we decided to work on this problem. Now, I learned a lot from working with the radiology people. In fact, I learned that breast cancer is a leading cause of death in the USA. Hundreds of thousands of cases are diagnosed in the USA each year, causing tens of thousands of deaths. Mammography is the hardest task in all of radiology. Radiologists miss a fifth of breast cancers, and half of women getting an annual mammogram over 10 years will have a false positive. And up to 3/4 of biopsies come back as benign. In other words, these are potentially unnecessary surgeries. So, if we can't even do much easier computer vision tasks, then this one is not going to work. But we couldn't do this alone. So like I said, I made some friends. This is my group. And then we extended this group to include Dr. Lowe, Joseph Lowe, and Fides, who is a radiologist. And then this is Yinhao, who's Dr. Lowe's student. And these are my students. Alina is leading this whole effort here. And I learned something from Joseph very quickly, which was that several AI algorithms have FDA approval for radiology. And I was quite alarmed because I was thinking, oh dear, oh dear. And as I told you earlier, some of them have FDA approval and then they don't actually work. All right, now I want to make a point that there are some problems that don't require interpretability, right? Not all problems require interpretability. So the problem on the left is breast lesion detection, which is sort of is there a lesion in this image? And for that, you don't really need interpretability because the explanation would be, I don't find a lesion. Like, great, thanks. Whereas over here, in this case, we have a lesion. We know we have a lesion, and we want to figure out whether to order a biopsy for it. And that we don't want that decision to be automated at this point. We really need to follow the radiologist's reasoning process because that decision is very, very difficult. Okay, so why is AI mammography hard? Well, first of all, AI radiology is hard. And as I showed you, it's not always reliable because FDA-approved deep learning algorithms are not performing well. Okay, mammography alone without AI is just really, really hard, as I mentioned. Third, we had no data. That makes things exceptionally hard. And then, even if we had data, we would run into this problem of confounding, where the algorithm would be right, but it's for the wrong reasons. And that's very hard to deal with. So it's maybe right because it's looking at some words written in the image rather than the medical content here. Okay, and then we also were trying to figure out how to design a system that would actually be helpful. And we noticed that everybody else in the whole AI world was doing malignant versus benign classification. And that actually, we found out from the radiologist, is not the right problem to solve. Because even if there's like a 2% chance that the lesion could be malignant, you're going to want to biopsy it. So for biopsy decisions, this question is not the right question to answer. The question is, should we biopsy this? Okay, so we designed this system that actually tries to sort of get at the core of this. Okay, so this is a black box approach. So the black box would say, all right, let's take this lesion. We'll tell you that its probability of malignancy is low. We'll predict benign because no reason. If we had done a saliency map approach, what it would do is it would say, okay, this is probably benign because blob, right? And it would just highlight the lesion, which is totally useless for us because we knew where the lesion was in the first place. That's why we asked the AI algorithm to look at it. So that does not help us at all beyond what we already knew. So we designed this method based on the prototype reasoning process that I showed you earlier, where the network says, well, and it sort of dissects the image. It says, well, I think this part of the image looks like this part of that prototype. And this has an indistinct margin. And so I'm going to add a little bit to the malignancy score because indistinct margins are more likely to be malignant. And then this part of the lesion looks like this part of that lesion, and that's circumscribed. And circumscribed, that's good for the patient. So we'll subtract some points from the malignancy score. Okay, so we designed this system. And while we were doing it, we found out that training it was incredibly difficult. So public data for training these things is completely abysmal. And this is shocking to me, given how important this problem is for human health, that you just can't get data to train it. The only public data that is really available are low quality images made with outdated equipment, and the labeling on those images is inconsistent. We found one data set that we thought we could use, and then we applied to get it. And they wanted us to hand over IP for whatever algorithm we designed from it, even before we had even done anything. And so we said, no, we're not going to do that. So this was shocking to us that these data sets are not available. So we ended up getting data from Duke, thanks to Joseph. And we were able to get a little over 1,000 digital screening mammogram images from 484 patients. And most people would look at these numbers and be like, what? You're training a deep neural network on that? Like, that's tiny. But it's actually even worse than that, because half of the data we couldn't even use because a bunch of it had like, microlobulated margins. There was only 41 of them in that class. There's no way we're going to learn anything from 41 images. And then 579 of them had obscured margins. So you can't use those. You have to retake the image. So we thought, oh my gosh, how are we going to do this? Well, let's try it, right? We had no other choice but to try. And so who should show up immediately was Clever Hans. And so the network was using information from healthy tissue and comparing that to the prototypes. That is not good, right? It's looking at just sort of like texture information in the image, which, could be a proxy for age or something like that. But that is not, telling us about that lesion, right? And we were like, okay, well, that's not good. But at least we successfully applied the interpretable machine learning technique without losing accuracy over the black box, which probably means the black box is confounded as well. But, okay. So then we thought, okay, well, let's not give up on this. And so we found a solution that allowed us to get more information out of our data, which was to do fine annotation. We created a little a tool where the radiologist would label parts of the image they were looking at. And then we penalized the proto-PNet algorithm and told it, you have to look here. If you're not looking here, you're going to be penalized. So in other words, we generalized proto-PNet to handle this kind of mixed labeling, the fine-grained sort of attention labels that the radiologist put in, and in additionally like standard labels. So when we did this, we still did not lose any accuracy over the black box. And it really helped us reduce the confounding because now the network looks in the right place. Okay, so after training this, we have 3 mass margin classifiers for different kinds of mass margins. So spiculated, indistinct, and circumscribed. And then we trained a malignancy classifier at the end, just so that we could see how we're doing. So I'm going to give you more detail kind of on just part of the network over here. I'm just going to look at the circumscribed classifier and show you how it reasons. So here, the network is taking the lesion, and then it's looking at different parts of the lesion, and it's saying, I think this looks like that. So this particular part of the lesion looks, with a similarity score of 4, like this prototype here, okay? So it is not a black box with an explanation. If it's wrong, you know exactly what the points were for each comparison that it made, and you can troubleshoot it in real time. You can also, well, if you're a radiologist, maybe if you're not, if you're not me, but if you're a radiologist, you can troubleshoot it in real time. And then also the information about what comparisons are not working, that allows us to augment the data set better so that we can troubleshoot it in the future. And then here is an example of a spiculated margin example where it's highlighting the parts of the image and again, comparing it to like a typical prototypical spiculated margin example. Okay, so the results from this are that, again, we're doing pretty well in the sense that we're not losing any accuracy over the black box. The black box gets to use the confounding information. We do not. Okay, so how did we deal with all of these things? Well, for confounding, the way we did it was with a fine annotation where we forced the network to look at certain places in the image where we knew the information was. So that would help it sort of avoid the clever Hans phenomenon. We didn't have data, but thankfully Joseph gave us some. This is not a sustainable solution. I think we should definitely be making public data sets available so that people can train their own networks on them. And then to solve the correct problem, we decomposed it and we would create interpretable models for each part. So we have a separate interpretable model for each mass margin classification. And then each of these classifiers use case-based reasoning. And what we did not do was use a black box model, try to explain it with saliency maps, and use it to predict malignant versus benign. That is not what we did at all. Okay, so for the last few minutes of the talk, I'm going to discuss the second approach to deep neural networks that are interpretable. And this method is called, for neural disentanglement. It's called concept whitening. And the method is kind of like principal components analysis for neural networks, okay? It takes the latent space and it sort of rotates it so that you can understand it. And so this is just the paper reference here. So as you know, CNNs are not naturally disentangled. So like you don't have a node that contains all the information that the network's using about airplanes. You don't have one node that activates when you have a car, right? The car information is spread all over the network. And people used to talk a long time ago about the idea of like a grandmother node. So whenever your grandmother shows up, the grandmother node would be activated. But you see, that's not how networks work, right? When your grandmother shows up, half the network highlights. So what we are trying to do is actually force only one node to be activated for each concept, okay? So to be clear, I'm not trying to get the network to classify airplane on the way to classifying airfield. That's not what I'm doing. I'm not creating little classifiers to go in here. All I'm doing is saying, if you are using information about airplane, I want it recorded through only this channel. And if you are using information about dogs, I want it recorded only through this activation of this node. None of the other nodes are allowed to be activated if you are going to use information about dog. Okay. So in other words, I am disentangling the information flow in the network. So if there's information about a concept, it has to go through that concepts node. Okay. So the concepts, as I mentioned, typically for black box model are all over the latent space. So if you look at like the latent space of a batch norm layer, and you look at where all the concepts are, highlighted, what people typically do is they try to figure out like, okay, which neurons are activated when I send like a dog through the network, and it might be that neurons 1 and neurons 2 are highly activated, and so what they've been doing is creating these concept vectors in latent space that sort of say like, okay, when neuron 1 and neuron 2 are highly activated, that's where, in that direction, that's where the dogs are, okay? But the problem with this is that these directions are not naturally orthogonal, because you can have like dogs and bridges that activate the same nodes, and you can also have like dogs being all over the latent space, and so when you point a concept vector in some direction, it doesn't actually capture what's going on. So anyway, these vectors are not naturally orthonormal, which is a problem. So we designed this technique called concept whitening that would replace the batch norm layer. And when this concept whitening module is added to a CNN, the latent space is decorrelated and normalized, so it's whitened, like white noise. And then we align the latent space with the concepts, okay? So you actually have one node handling all information about airplanes. Okay, so I'm going to show you a couple slides next that look at images that are like the extremes of these axes. So I'm going to walk out to the extreme end of the airplane axis and the extreme end of the bed axis, and walk to the extreme end of the person axis. All right. So, when the network, here's what happens when CW is added to different layers, right? So I'm going to add CW to layer 2. And at the second layer, the airplane node actually gets really excited about fish and bugs. Okay, so remember the CW, it just forces all the information the network uses about airplanes at that point to go through only one node. And it can't really learn can't really represent the actual information about an airplane in 2 layers. So what does it do? It creates a primitive version of airplane, and this is what it thinks is the most extreme version of airplane. It's a blue background with a gray or white object in the middle. Okay, and then if I walk to the extreme of the bed axis, I see kind of bright colors. And then for the person axis, I see sort of like stringy textures. And so in earlier layers, color and texture information related to the concepts is represented along the axes. And then if you look at the kind of later layers, if you do CW on the 16th layer, it's actually really representing what an airplane is and putting that information along the axes. So the axes are now kind of pure concept vectors. So I have an example here that shows how an image travels through the layers. So here's like this beautiful bright orange sunset. So of course the network gets, early on, it gets really excited and thinks it's a bed because it has orange in it. And it doesn't think that it's an airplane because it's not a blue object with a white with a white object in the middle. So anyway, it starts off highly activating the bed node and not the airplane node. And then as we go through the network, it's starting to think that it's less and less like a bed. And then eventually it's like, wait, I see some blue sky with clouds. And I have enough information to be able to do that. So it's less highlighting the bed node and more highlighting the airplane node. And then it kind of gets confused at some point because it's like, well, is this a bed or is this an airplane? I don't know, because it doesn't seem to look like either one of them. But anyway, so it eventually decides it's closer to the airplane axis than to the bed axis. And then eventually, sort of when it converges, it's like, this is not a bed. It might be an airplane, but it's not a bed. Okay, so the advantages of this over batch norm are that it doesn't sacrifice any accuracy. Accuracy is on par with standard CNNs, and it's really easy to use. You actually start from a pre-trained model and do one additional pass through the data. It does require some additional data to define what the concepts are, but it disentangles the latent space essentially for free. All right, and so back to this. What I've just shown now is that you know, the prototype networks that I've shown to you that do case-based reasoning with fine annotation, they're strictly better than saliency maps because they don't just show you where the network is looking, they show you what the network is doing with that information. And then the concept whitening is strictly better than concept vectors because it disentangles the latent space and puts the information you need along the axes. And it's inherently interpretable instead of just explaining a black box. Okay, so the takeaways are that there's really no scientific evidence supporting a trade-off between interpretability and accuracy in deep learning. Interpretability actually helps you troubleshoot, and it actually helps accuracy. So the trade-off everybody's always talking about, I'm not seeing evidence that it actually exists. And also, it's just a matter of time until companies try to use black box models for biopsy decisions. And so I'm trying to kind of head that off by proposing an alternative in advance. So it creates kind of like a standard that people can sort of ask for. They can say, no, I don't really want that. I want to do something like this, right? Because I know it's possible. All right, and this is all the papers that I've spoken about. This is the Stop Explaining Black Box paper. This is the concept whitening paper. This is a review paper about interpretability that we just published. And then here is the case-based reasoning method. This looks like that, and then its application to digital mammography. All right, thank you very much.
Thank you. Well, there are a lot of questions. If you want to take them, or
sure. Okay. So let me just grab here. I'll pick. I get to pick my favorite because I'm looking at the questions.
Right.
Okay. Is the case-based reasoning driving the classification? So we've modified the fundamental architecture of the DNN, or is it explaining the classification? Now here, we've actually completely modified the architecture of the DNN by adding an extra layer before the last fully connected layer. So it's actually forced to do case-based reasoning. It has no choice. It has to reason about cases this way. Okay. Let's see here. In the this looks like that approach, is it fair to understand this method as use the neural network to determine important areas of the image, then use the similarity comparisons to make a prediction? So the neural network is really used for reducing the search space over the image to focus similarity computations on. So the neural network not only does focusing the search space over the image, it's actually deciding where in the image it needs to look and what to do and what similarity comparison to do. And it's deciding these things at the same time because it's actually doing kind of a search over the image to see whether this prototype looks like any part of that image. So it's doing both of these things at the same time. And people often ask me, like, what is the similarity metric it's using? And the answer is it's using L2 distance in the latent space. That's the similarity metric. But luckily, a human doesn't have to understand that because they can visually determine whether this looks like that. So we're depending on the human's visual system to verify that the comparison is correct. Okay, let's see here. I'm getting a bunch of questions that I've already answered, like, do you lose accuracy? And I said, no, we don't lose accuracy, because otherwise I wouldn't really be presenting that. We'd still be working on it. Okay, the vision examples all seem to be based on local patterns. What happens when evidence is not localized? So the concept whitening network does not rely on local information. So that network, if you want to disentangle textures, we actually have some examples in the paper where you're putting like wood texture along one axis and like, I don't know, whatever texture on a different, blanket texture on another axis, and then that's not localized at all. But the case-based reasoning stuff, that does use local prototypes. That is based on using local information. We also have a paper where we constructed sort of hierarchical prototypes, but we're still, that's a topic that, believe it or not, we're still working on. Okay, to do anything to ensure diversity in the parts of the input image chosen. So we don't do that. It says, if not, could a model learn to use the same high scoring comparison 20 times to achieve a high score in the correct class? It could certainly do that, but then it wouldn't be using its predictive power very well, because then it wouldn't have extra prototypes to really understand the full class. So in other words, what I'm saying is what you're suggesting, it's actually possible for that to happen, but the network would sacrifice performance to do it, and then that would be optimized out during training. So it's very unlikely that this actually happens. Okay, let's see here. How do you know that the fine annotation by humans is not actually cutting out real information, not just confounding information? One of the advantages of machine learning is that it can identify real patterns that people don't see. If we restrict models to looking at only what people think is important, don't we run the risk of losing key insights? So that is a very good question. So the radiologists have assured me that if you go way outside the lesion, this is healthy tissue, right? So we know that in cancer therapy, like when you remove the lesion, you're actually removing the actual part that's causing cancer. But there is confounding information outside of the lesion that it's possible that it's relevant for predicting whether the lesion is malignant. For example, what if it's a proxy for age? The problem is that when you allow that extra information, you're also allowing information like, what kind of equipment did I take the image on? And other things that it really should not be using. So radiologists are trained for years to be able to read these images, to really be able to understand the physics behind what's going on. And that's kind of fairly well understood at this point. And I think if you're going to sort of say, well, now we're allowed to use all kind of other stuff, then you're opening yourself up for models that don't generalize beyond the data set you trained them on. Okay. Let's see here. Can the explanations be used to improve the performance of the underlying black box neural network itself? So there is no black box neural network itself. So I don't understand that question. Or by some more focused variant of boosting. So that's a good question. So the way I'm reading that question is, if we have the explanations, can we use it to develop features that we can use for sort of boosting, right? Instead of like using a neural network. And the truth is that the features that we find, they're actually being combined in a linear model, right? Boosting, if you do boosted decision trees, that's complicated, but you could boost and create a linear model with boosting, and that would be fine too. But yeah, so in other words, we're doing something simpler than boosting, right? It's just a linear model at the end. If the human disagrees with one part of the case-based reasoning, can they use the model to predict what the classification decision would be without the error made by the model? And that's exactly what we're trying to figure out now. So we're actually, our radiology team is conducting like a human studies experiment to try to see whether our network can help train radiologists. So even if it's wrong, maybe there's something valuable in the reasoning process that the radiologist can look at and be like, oh, it's looking at that. That's wrong. I'm going to ignore that and like pay attention to the other things it's doing, because those are actually valuable for me. So yeah, even if the network's wrong, I think it can still be valuable. Can concept whitening be used for hierarchical classification or reasoning? That is a good question. I don't think anyone's tried that, and that is a great research project. You could make it your PhD work or whatever you like. I don't know. Are you working on any user studies with radiologists with the concept whitening approach? We're doing that for the proto-PNet approach to see how interpretable users find the approach. Yeah, so that's what we're doing now with the radiologists. So we have a team of people designing a user interface, and we have the radiologists kind of informing us what questions, how to display the information so the radiologists can understand it. And I'm really curious what they'll say, since, like I said, I can't read these images at all. It's just completely, for me, it's like, maybe if it's obviously speculated, I can understand it. But like, for me, but I can understand how people could find it valuable, right? Because like, this lesion looks like this lesion in this way that I understand, right? As if I was a radiologist. Okay. Let's see here. Is concept whitening still useful when there are fewer classes? Okay, so this is a great question, because what you can do is you can provide concept data sets. Like you have to tell it what the concept is by showing it examples of that concept, right? So you showed a bunch of airplanes. You say, this is the airplane concept. This is the car concept. And you can do as many or as few concepts as you want. So you can, let's say you have, say, 20 nodes in that layer, and you want to make the first one like a car node, and the second one a dog node, and the third one an airplane node. You can do that, and then you can leave the rest of the nodes free. Now, when you do that, all the airplane information still has to go through the airplane node. None of the other nodes in that layer are allowed to highlight on airplane information, are allowed to, yeah, they're not allowed to use any airplane information, okay? So you can do as few or as many concepts as you want. You can even mix up like airplane, car, and then some texture, right? You can do that and force it to reason about it that way, and leave the rest of the nodes free to do whatever they want. Okay.
So let's take one more question, because the time is 12 o'clock. So pick your last question.
All right. If I understand correctly, in concept whitening, the concept should be known and labeled in advance. Is there a principled way to choose relevant concepts? And that's the question that kind of haunts a very large number of computer vision researchers. In our review paper, we point out that there is, like, one of the holy grail problems in computer vision is to be able to discover these concepts automatically. And so that's something we're actually working on. But it's much, much more difficult. It's much easier for the network to do a good job being interpretable if you tell it, okay, airplanes look like that, okay? And then it can sort of like, okay, fine, I'll put all airplane information along this one axis. Just much easier.
So I want to thank you very much, Dr. Rudin, for a wonderful talk. I think it's very thought-provoking. It's very, you're obviously operating on the leading edge of AI and interpretability, and just the audience, I think, is very much receptive to it. So thank you so much. I appreciate your talk.
Thanks. It was a great audience. Lots of great questions.